So a matrix is just an organization of numbers put in a box, is basically the way to say it. You've got rows and columns. If you think of columns like this, Roman columns, you'll know that columns go up and down and rows go this way. That's important. So when we're going to have a box of numbers, this would be a matrix. And that matrix has 3 columns and 2 rows. So it's a way to organize data. It's a way to organize data in a way that you can write less. Mathematicians are inherently lazy. They're always looking for ways to write less things. So if they had the following system of equations, they may choose to write it as a matrix. And they might even add a line here to say, oh, there was an equal sign there before, but I don't want to write equal sign. A line is much quicker. Well, by writing the x's first, you know that the first column is x's, the second column is y's, and the third column is just your answers. So as long as you have your data organized in a way, you could throw it into this and then take away some of that extra information so you don't have to write it over and over again. And that may make your life easier, or at least cause you to write less things. Especially if you had, okay, we solved, for those of you that were here, we solved a system of 4 equations and 4 unknowns. That's a lot of variables to deal with all the time. So we're going to learn how we can do the same kind of math that we did before, but using matrices and only worrying about the coefficients of those equations. So again, horizontal is rows, the vertical entry are columns. And then we get our dimensions. So for example here, your dimensions are always the number of rows by the number of columns. And if you just really like matrices and think of the slogan, Matrices Rock, then you'll always remember it. Because you've got rows first, then if you spell columns that way, you have columns next, Matrices Rock, and then you'll always remember which to put first. So this one has 3 rows and 4 columns. Columns, that's how you have to say that. Help you remember. And then that'll be a 3 by 4. So the dimensions, we sometimes call it the order. So there are 3 matrices. Quickly underneath, write the dimensions or the order of those ones, and I'll put up the answers. This is a 3 by 1. Remember, this is your columns. Columns go up and down. You've only got one of them. And this one is a 4 by 3. And this is a 1 by 4. So we use capital letters to denote our matrices. So in that last example, when I was titling each of those matrices, I had matrix M, matrix P, matrix S, and I used capital letters. And then we use little letters or smaller letters to show the entries. Okay? So for example, on this last one here, if I picked this 6, I would call that entry P, row 3, comma, column 2. And I use a little p because my matrix is big P. So that's, if I was trying to find little p, 3, 2, that would tell me go to row 3, column 2. It's equal to 6. Okay? And I've seen some textbooks take out the comma. Just do 3, 2. Because if the matrix isn't that big, it's obvious the first number is your row, the second number is your column. But I guess if you had a really huge matrix, it would make sense to put the comma in there. It's just to show that when we're talking about like this one right here, I would call M11 because the matrix is M, and then each element, each item inside, I would label with a little m. So if I said, what's M13, you'd say it's 6. What's S14? Well, you'd go to this matrix, and it would be the fourth one, which would be a 4. So it's just sort of definitions right now for getting us used to what we're talking about. And again, the row is always first, the column after, so just remember the slogan, that Matrices rock, and you'll be fine. So here's a matrix. This would be matrix A because all of our elements are listed with little a's. And the main diagonal of the matrix is this one right here where you have 1, 1, 2, 2, 3, 3, 4, 4, and so on. So there's the matrix M. Quickly find out what each of those things are and write down the order. All right, did you get 0, E, pi? And the dimensions of this is a 3 by 4. Rows first, then columns. Now, a column matrix has only one column. A row matrix has only one row. A square matrix is in a specific shape. Any guesses? Oh, a square. Nice. So if it has the same number of rows and columns, all 4 of those examples are square matrices. A zero matrix has all zeros. So you could make like a 8 by 8 zero matrix by just filling an 8 by 8 square with 64 zeros. And an identity matrix is a square matrix where on the main diagonal there's a 1. So what we're doing right now is we're setting up some definitions so that we can do math with matrices. And we can do some of the same math that we've done with everything else that we've had so far. But we're going to learn that some math is different than what we've done so far. So we're going to be able to add matrices. And what do you think happens when you add the zero matrix to a matrix? It doesn't make a difference, right? Just like adding 0 to a number doesn't make a difference. Okay? We're going to need to figure out when we're multiplying how when we multiply by 1, something doesn't change. That's going to happen in matrices as well, but we need to figure out what that 1 looks like. And that's this identity matrix. Now when you multiply by an identity matrix, you get the same answer that you had before. But our 1 looks different than what we're used to. It's not just a number 1. It's a diagonal of 1s and the rest are zeros. Ooh. All right, I have a little puzzle in between. Here's the puzzle. All of those dots are your pets. You have pet dots, they're alive. Okay? And this is looking down at your pet dots. And unfortunately, your pet dots don't get along with each other. So right now, if they're in that same pen, they will all eat each other up. And you'll only have probably 1 dot left, and you'll be sad because you bought 9 pet dots. And they all... So you decide you better take this pen that you have them in and separate them into separate pens. Now you could do that easily if you had lots of pens. You could just separate it with lines. Does this erase? Good, it doesn't. Okay, so I could just separate it like that, right? And then they'd all be separate and everything would be good. But you want to be creative and you look around and you only have things in the shape of squares in your house to make pens, and you want to separate all 9 of those dots into different pens using only 2 squares. Okay? So you got 9 dots there. You want to separate them into separate pens, and you can use 2 squares. Back to matrices definitions. The transpose of a matrix. You just interchange the rows and the columns. So for this first one, the transpose, it has 4 rows, 2 columns. Now you're going to have 4 columns, 2 rows. So you got 4 and 3, 2 and -1, -1 and 5, and, oops, I got a little crazy there, -1 and 4, 5 and 7. So notice that your first column becomes your first row, and your second column becomes your second row. So your GT would look like that. All right, so now we get to do some mathematics. The very first mathematics is adding and subtracting. And adding and subtracting is really straightforward. You just add or subtract the corresponding elements. So the important thing is that you can't just add any matrices together. If 2 matrices are different sizes, you actually can't add them together because there needs to be corresponding elements in order to add them. So in this first example, we have a 3 by 3 here and a 3 by 3 here. Since they're the same size, you can add them together. And so it's just a ton of little mental math things that you'll do. You'll do 1 plus 0, 3 plus 0, 1 plus 5, 1 plus 7, 0 plus 5, 0 plus 0. Put them all together and get your answer by adding the 2 together. And then you would just write a double digit in that spot. Scalar multiplication, what that means is you have a number in front of your matrix. So here in my example, I have 2 times that matrix. What's going to happen is that number is going to multiply by everything inside. So that means you'll do 2 times 1, 2 times 8, 2 times -3. Here's your answer. It also means that if every single element in your matrix has a common factor, you could factor it out and write it as scalar multiplication in front.